Congratulations on making it through the first 2 chapters of Calculus 2. We're moving on to Chapter 7, and we're getting back to some integration techniques. And I just wanted to remind you of some of the basic integrals that we know already. This chart is on page 475 in your textbook. And like I said, these are ones that we theoretically already knew, although I wanted to point out a couple here, actually these 4. These 4, hyperbolic sine, which is abbreviated SINH, and hyperbolic cosine. We didn't really do those in Calculus 1, and we're not really going to do them in Calculus 2 either. Problem 17 on your homework uses one of these once. So I just wanted, without diving into what they are, I just wanted to make you aware of the rules. And they're pretty straightforward. The derivative of hyperbolic sine is hyperbolic cosine. And then derivative of hyperbolic cosine is hyperbolic sine. So the integrals are just backwards from that. And if you didn't pick it up, when we did u substitution, we did tangent as sine over cosine, and did u as the cosine, u as the cosine, and we got 2 more integration rules here. So basically these are our integration rules, and then we have one sort of general technique so far, which is u substitution. What we don't have so far is some sort of way to integrate something like x times sine of x. We know how to integrate x. We know how to integrate sine of x. But as you know from derivatives, having a product is a whole different ball of wax. And u substitution isn't going to help us here. So we need some sort of way to reverse engineer a product rule. We need an integration product rule. And that's actually what we're going to get in this section, this integration by parts. So let me remind you of the product rule for derivatives. There's lots of different ways to notate this. I'm using f and g, and I'm using it without the of x on there. But this is the integration by parts. Basically says if you have 2 functions multiplied, the derivative is the derivative of the first function times the original second function plus other way around, fg prime. What I'd like to do now that we know about derivatives, now that we know about integrals, is just take the integral of both sides of this equation and see where that gets us. So let's get on the right layer, and let's integrate. Integrate that side, integrate that side. We know fundamental theorem of calculus, integral and derivative undo each other. So this side just becomes fg. And we know on the other side that integral of 2 things added becomes separate integrals. So I'm just going to write this as integral f prime g plus integral f g prime. And I just want to solve this equation, I think, for this term right here. So let me move that to one side, or let me move this term here to the other side. So the integral of f g prime is equal to f times g minus integral of f prime g. Okay. This is the integration by parts rule. And it says that, let's look at what we've got. It says that if you have an integral of 2 functions multiplied, you identify one of those functions as just being a plain function, and you look at the other one as being a derivative. And then we know how to get the results of this integration. We say it's the f function and the non-derivative version of g, or the integral of g prime, and then minus a particular integral. So this means we're rewriting one integral in terms of another integral. Hopefully this integral is easier. That's what we hope. So our idea is to trade a difficult or undoable integral for an easier integral. There's also a change in notation that a lot of people like here, and I don't know why. F and G are just fine, but sometimes people like to write F as U and G as V. So they write the derivative of G as dV. So they say U dV, and then that would equal U and V minus the integral of V du. And notice I switched the order on the F and the G. But I think the only reason that people really like this is they get to use the mnemonic device to help them remember this, which UV, of course, is the abbreviation for ultraviolet. And then VDU is definitely voodoo. So if this makes sense to you, or if this helps you remember, use it. And if it doesn't make sense to you, ignore it. But a lot of people remember integration by parts as ultraviolet voodoo. And that doesn't tell you everything. It doesn't tell you there's a minus sign here or an integral sign here. But let's take a look and see if we can just use this for one or two examples. So let's see if we can do, as an example, let's just see if we can integrate x times sine of x. And our first goal here is just to recognize that we do have a product. We do have this sort of form where we're saying, yep, got a function times another function. I need to decide which one of those I'm going to look at as f and which one I'm going to look at as g, or to use this notation down here, which one's going to be u and which one's going to be dv. So I'm going to decide, and I'll tell you why I'm deciding this in a minute, but for the moment I'm just going to decide that u is going to be the x function. And dv then will get to be sine of x, and since it's a derivative, I'll put the dx on there. Notice by the time we get done doing ultraviolet voodoo, I will need to know what v is. Right now I just know dv. And I'll also need to know du. So notice I'm picking two of the pieces. I picked u and dv, and I'm going to calculate two of the other pieces before I even start trying to write ultraviolet voodoo. So if u is x, the derivative of u is 1. And I'll put the dx on there just for completeness sake. So that's derivative, this direction. And then dv is sine. So the integral of sine will be v. Keep in mind the integral of sine is negative cosine. Okay, so now let's see if we can rewrite our original integral. I looked at it as being u dv. So the integral of u u and dv should be equal to ultraviolet. So there's ultraviolet, x times negative cosine of x. Ultraviolet minus the integral of voodoo, so v du. So v negative cosine x, du is 1 dx. And we hope that this integral is easier than the one over here. And our hope is not disappointed this time around. This is an easier integral. So let's finish cleaning this up. So this is a positive times a negative, so it'll be negative x cosine of x, double negative here, so that's a plus integral cosine x dx. And now we can finally see, yes, that is indeed a much easier integral than the one we started with. The integral of cosine is just sine. And of course, because this is an indefinite integral, we will not forget the plus c that we haven't seen in a while. But this is the integral of x times sine of x. You can probably take the derivative of this. You need a product rule right here. Take the derivative of it yourself and just see that a couple pieces cancel, and that what's left over after you do the derivative of all of this is just x times sine of x. All right, there's more to unpack here, so we'll do a couple more examples in the next video.